All right, diamagnetic. Got him. Good. No. Let me ask you, so N2 minus 1. How many electrons does N2 minus 1 have? 9. What does that tell me?
9 arrows.
It's going to have 9 arrows. Are we going to have, are all the electrons going to have a buddy?
No.
No. So this has to be para, right? What about the second one? 11. Is everybody going to have a buddy?
No.
So that's going to be para. You see, we don't actually have to draw the figures for these, right? If I have an odd number of electrons, that means at least one of the electrons are going to be not have a buddy, so we're going to have somebody unpaired.
I mean, like with the numbers of electrons.
Oh,
Hermione.
yeah. So N2 is, right, 5 and 5 is 11. N plus 2 is, there we go. All right, we're all happy now. Life is good. O2 is paramagnetic. Why is that? Because that's what I... Well, let's do O2, right? I've got, let's do our little chart, right? Remember that? So I've got 2s. This is sigma 2s. This is anti-sigma 2s. Y'all okay? This is sigma 2p. And this is anti-sigma 2p. This is pi 2p and pi 2p. And this is anti, right? Total oxygens together, how many? There's 12 electrons. So let's count them. I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And so we see, without thinking about bond order or the other stuff, we see I've got 2 that are unpaired. That's going to lead me to paramagnetic. Paramagnetic. All right. Do the same thing with nitrogen. Nitrogen should have 10, right? Okay. And if nitrogen has 10, it's going to look like that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And everybody's got a buddy. Everyone is paired, so that's going to make it diamagnetic. So if it's odd electrons, you know it's got to be paramagnetic because somebody's going to be alone. And then otherwise, sketch this real quick. And I don't see that you're going to have a lot of, you'll probably have basically periods 2 and 3 are what they're going to ask you questions over. You could have some really weird one, but if you get anything at all, it'll just be simple period 2 and 3. So we're not going to get into the other stuff. All right, so just, it's a conceptual thing. We just need you to start working through. Cool. Good? All right. Which of these following statements is false? We just did some problems that should help you. this true or false? True or false? Y'all okay with that one? We just talked about that, right? Okay. If I've got an odd number of electrons, it has to be paramagnetic, yeah. So that's not going to be it.
How is the first one not true? Oxygen.
Because not every single one. Yeah.
This is no. I thought it was true. This
We
is
just did oxygen.
Oxygen
Not
has
ev-
12 and
Yeah,
it's
it has 12.
diamagnetic. Huh? I'm gonna say
Oxygen has paramagnetic.
So oxygen has 12, right?
yeah.
And it's what?
Paramagnetic.
And nitrogen has 10, which is, and it's
Diamagnetic.
so.
Oh.
Yeah, just
As an absolute statement, this is going to be false, right? But anyway, let's keep coming. Paramagnetism cannot be deduced solely from the Lewis structure of a molecule. Paramagnetic molecules are attracted. Also true. Good deal. Y'all okay?
Diamagnetic is
Diamagnetic repel.
Can you go over what makes something diamagnetic?
Diamagnetic means you have what?
paired electrons.
Paired all electrons have all the orbitals are paired, right?
What do you mean, say paired? Does that mean it has like two?
Like arrows, like
Up and
going
down.
up and down.
It has an up and a down.
If it's just up, then it's
This is unpaired electrons,
that's diamagnetic,
right?
not paramagnetic.
Right.
Okay.
And for molecules, you've got to do the molecular orbital diagram to determine that.
Neon was diamagnetic and nitrogen was paramagnetic.
Yeah, that's what I meant.
Then it was backwards.
Oh, she said, yeah, that's unpaired electrons, paramagnetic, paired electrons, diamagnetic. It's okay. All right, heteronuclear. Hetero means different. Yeah, it gets even more fun. All right, this is special cases involve molecules that are adjacent to each other in the periodic table. Okay.
Shivering in fear.
I don't even think that these are in your notes, are they?
I think heteronuclear is.
That is so
Heteronuclear.
diatomic.
Well, you read the chapters and you outlined the chapters and you took notes on them,
Yeah.
so you're good with that.
Yeah. Heteronuclear diatomic molecule.
Yeah, there you go. All right. So it works the same way. It's just instead of people coming in with the same energy levels and the same, you're just multiplying by 2 however many electrons, right? I'm just going to figure out what each one has. So I could look at something like NO plus or the cyanide ions, and we could take a look at that. And we said, well, this has 10 valence electrons. Okay, this has 10 valence electrons. Both of them are diamagnetic, and they got a bond order of 3. We've actually done both of these models. We know how they work, right? Okay. So this is how they line up, and I know that because we got 10 valence electrons. I've got 2 atoms with 10 valence electrons. All of them are going to look like this. I've got 2 atoms with 10 valence electrons. That's what they're going to look like. I just have to do this once for either of these. It doesn't matter. All right. Now again, I fill from the bottom here. All right. When they're very different, you can't use this. They take on a different type of structure. So they've got to be sort of similar before we can use this heteronuclear approach. All right. Yeah, I'm going to skip that. Other than to say, see how it looks different? Yay. So, and again, we know this with what's the deal with hydrogen and fluorine? What's really different? Yeah, it looks a lot. It ends up acting a lot like an ion, right? It is an acid. It's hydrofluoric acid. Yeah. Is it a strong acid?
One way but not to eat.
Is it a strong acid?
No.
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 Because it's holding on to the hydrogen tightly.
And that's exactly right. This fluorine and this hydrogen are actually holding on to each other so tightly that even when water's around, they're not going to fall apart.
They're best friends.
I thought that mean then they're strong.
Remember, strong falls apart easy.
Oh, okay.
Just remember that. All right. So we can do some energy level diagrams. You just need to understand that the electron pairs are not going to be shared equally. There's an electronegativity difference of like 1.9, I think. Fluorine's 4, hydrogen's 2.1. Even though hydrogen is electronegative, the electrons are basically spending their time over there. Because of that, if I were to imagine visually a picture of where the electrons are spending their time, they're basically spending all their time with fluorine. And then the hydrogen acts kind of like a proton and just sticks to the fluorine. Just sticks really, really tightly. Okay? Yeah, and this is a picture that I was talking about. You can actually take pictures and you can see if they're taking a picture, the electron can be found here, but in terms of probability, you'll see that the electron that's shared is really spending much more of its time near fluorine.
Do they have actual pixels?
Yeah. I mean, not like it's a computer-generated overlay, but yeah.
So it's not a picture.
Well, it's not a Polaroid. Somebody didn't take their iPhone and, right? But yeah, it's a computer-generated image, but that's what's showing what's going on. And actually, these nuclei are inserted there. They're just empty spaces. Okay? All right. So we can look at this. I'm going to skip that. So this is what I want you to think about. Localized electron. How do I put these two pieces together? Again, your test, and I want you mentally thinking more about the localized model. But I want you to think about the sigma bonds. You can think about those as localized. Those don't change. The electrons are in the same path. They line up between the two nuclei. They're going to be found there. They're easy to think about being associated either equally between the two or more with one versus the other. The pi bonds, though, if you'll recall, the pi bonds are running either across the top away from the nuclei or on the sides away from the nuclei. So you have to think about those as delocalized. And then for molecules that require resonance, I can talk about the localized model in terms of the sigma bonding and the molecular model in terms of the pi bonding. And that, again, I think we've talked about that enough. I'm hoping you're getting a visual image about how those extra bonds work, those pi bonds there. All right. So I'm going to say this, and then we're done. You may see these structures. Somebody mentioned on some of the practice tests seeing these structures. That's fine. I do want you to know if you see a dot there, when you get to, that just means carbon. If you see an intersection of lines and nothing annotated there, that's carbon. Okay? Sometimes you'll see these structures like this with just straight lines out or nothing at all. And you'll need to know that a hydrogen fills in that.
What are the lines on the inside of the...
What is it?
That's what I was...
It's a double bond, yeah. Yeah, so you can do your C, and 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 your C. And that's a double bond, and a double bond, and a double bond. Okay, there's your benzene ring. Now, all of these have how many, every one of these carbons has how many bonds?
Two. They're all three.
Each carbon has how many bonds? 3. And so they all need. Right, so if I drew that like that, your brain would have to go, there's a hydrogen hanging off of each one of these. And I can draw it like this too. Okay, you'll see it like that. This means the same thing. Now typically for your test, I think you're going to see them all like this. We'll actually point out each of the, I don't think you're going to see them there. But you do need to understand, if it's just benzene, there's a resonance structure that these double bonds, each one of these bonds is like 1.5, yeah.
So that thing down there,
This one?
all the H's, the little intersections, those are carbon.
Yes,
Oh.
that's what I was saying. You may see this right now, and from an organic chemistry perspective, you need to know that that's a C, that's a carbon. Because in organic chemistry, everything's carbon, so we just quit being redundant. We just write carbon on there, okay? And again, a lot of times you'll see this structure, and you know that's benzene, all right? But I'm not even bothering to write the extra hydrogens or the carbons.
So is that a C?
Yeah, this is a,
Right there is like
that's a carbon, 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 carbon. But you notice that's nitrogen. I got to tell you that's different. Okay, and then that one's nitrogen. Yeah, the intersections with no letters are carbon. Good? Okay, so you can actually, yes?
Does CH3 have a name?
Uh-huh. So what's CH4?
Methane.
CH4 is methane.
CH4 is methane.
So CH3 is methyl. It's called a methyl group. So like methyl chloride is CH3Cl.
Methyl chloride.
Methyl chloride.
Or if you take the Cl, erase it, put neon. No, you can't do that. Put F. You say methyl fluoride.
Yes.
Good job, yes.
We're learning.
Yeah. Sometimes. All right. So you will get questions like looking at this molecule. I'm going to look at this one, and I'm going to say, this is a terrible one to look at, but it's not even drawn right. Okay, I'm going to say, okay, looking at that carbon, what's the hybridization on that carbon?
SP3.
How many, looking at this carbon, how many regions of electron density do I see? 3. 1, 2, 3. This is sp2. Okay? You'll get questions like that, and a lot of times students, particularly AP chemistry students, they'll see these structures and they'll go, that's organic, my teacher didn't teach me organic. Like, just calm down, read the question. Yes, that's a benzene ring. That's not what the question's asking you. You can answer that question. Okay? Right?
So are we going to start drawing those?
You probably not.
Okay.
Probably not until organic. Back in my day, we actually had to buy a little piece of plastic template with all the different structures, little triangles, and yeah, there you go. Yeah, so if I wanted to draw this, you'd have to have a resonance structure, and this is the two you draw. Just mentally understanding that these structures are equivalent, that these double bonds, even though locking everything in place, these double bonds move between them.
The name change. This is completely.
No, not
random.
no. It's yeah.
It's completely random. Like when you chain them, do the names change?
When you do what?
Like when you. Cause I remember there was something I read on the textbook thing where if you were to remove one of the hydrogens add a carbon, then.
Oh yeah, yeah. That totally changes everything.
Oh gosh.
Yeah, yeah. So this you'll start with benzene and you'll start hanging stuff on it, and then you'll put a nitrogen on it. That'll change things, and then you'll hang a nitrogen off of one of them. Then that nitrogen will become number 1, and then there'll be an oxygen over here on number 3. Anyway, it's all good fun stuff. Yeah, this is all right. So these are the questions you might be asked. Okay, this is this. Okay. Well, this is the pretty picture that's going on, right? I've taken the 4, the S and the 3 P's, merged them into sp2 hybridized. These are all equal orbitals. Okay, I now have only 3 orbitals, and I'm sharing one of these with a carbon here, one of these with a carbon here, and one of these with a hydrogen. All right. Each of these carbons is sp2 hybridized, and you can see the P, right? The one that's not hybridized is perpendicular to the plane, and that's being used to double bond here, and double bond here, and double bond there. All right. And that's another way to draw benzene.
That's a confusing way.
So this means I don't have to do a resonance structure. This is why I start with, if I do benzene here like this, everyone knows, oh, he's talking about benzene. It's got 6 hydrogens, 6 carbons. Oh, yeah. Yeah, yeah. And this indicates delocalized pi bonding. Yep, that's it.
Why didn't put
Yes.